Imagine having the power to predict the future. What would you do? You could anticipate when equipment might fail, improve warning systems for severe weather, or ensure there are enough planes for a given flight route. That's the magic of time series forecasting. In this video, we'll explore how forecasting lets us recognize patterns in time series data to make predictions. Before we can start forecasting, we need some time series data, and data can be messy. One big challenge is that to make predictions, data often need to be evenly spaced. But in the real world, measurements aren't always perfectly timed. To fix this, we can resample the data to get consistent intervals, filling in the gaps with methods like linear interpolation, nearest neighbor, or regression-based techniques. When working with multiple time series, like data from various sensors, it's important to align them on the same time intervals, and similar techniques can be applied to align the entire dataset. Timing isn't the only characteristic of time series data you need to be aware of when preparing your data for forecasting. Anomalies or unexpected events sometimes occur, like a sensor going offline or sudden spikes and drops, which might indicate unusual conditions like a malfunction. You may notice a trend in the data, which could reveal patterns like gradual wear and tear on equipment or a steady increase in energy usage. Seasonality, or repeating patterns at regular intervals, such as daily temperature changes or energy consumption spikes in the morning and evening, can occur. Noise is also common. It's exactly the way you think of it, background noise, often caused by environmental interference. Understanding these characteristics before forecasting is crucial, and you may want to remove outliers, detrend the data, or apply smoothing techniques before carrying on. We've been talking about time series in the time domain, which seems reasonable. But let's briefly step into the frequency domain, which may uncover hidden insights. By viewing data as cycles or frequencies, we can reveal trends and recurring patterns, like seasonal variations or irregular cycles, that might not be obvious in the time domain. Now, wavelets are particularly useful for analyzing complex signals with multiple scales, capturing both high-frequency details and broader trends. They're ideal for time series data with sudden spikes or varying patterns. Both frequency domain and wavelet analysis are often used to extract features from machine learning, to better represent the signal and capture the more intricate patterns for training the model. Now, what we've all been waiting for, let's explore different methods for time series forecasting. Let's start with the most straightforward approach, statistical methods. Two common statistical techniques for capturing trends in time series forecasting is regression and ARIMA. Regression is useful for identifying steady trends, while ARIMA is effective for handling data with trends and seasonality. Both methods are valuable tools for understanding and predicting patterns over time. Our next forecasting method is machine learning. Unlike statistical techniques that handle data sequentially, many machine learning models treat time as just another feature, allowing us to create patterns from past observations without following the order of events. These are generally regression models, adapted and expanded to include more complex algorithms to identify relationships between variables. One useful model is support vector regression, or SVR. This is an adaptation of support vector machines and works by finding a best fit line within a margin, making it effective where data is noisy or nonlinear, like predicting sensor readings. Since SVR doesn't naturally account for time dependencies, the time can be represented differently. This approach allows SVR to capture complex patterns, though it may struggle with changes that happen over longer periods. Finally, let's explore deep learning methods, which excel at capturing the patterns in time series data. These models are really good with data that have long-term dependencies. One of the most popular models for time series forecasting is the long short-term memory, or LSTM network, which is designed to learn from sequences and capture long-term dependencies by selectively remembering and forgetting information. This makes LSTMs ideal for sensor data, where past readings can strongly influence future values. LSTMs usually require minimal data preparation, since they can identify trends, seasonality, and anomalies directly from the data, allowing for more nuanced forecasting without as much time up front. Another approach is the transformer model, which has gained popularity for handling time series data, especially when there are complex interactions over long sequences. Unlike LSTMs, transformers don't rely on sequential processing, which allows them to capture dependencies between any 2 points in the data, regardless of distance. Transformers are really useful when dealing with large data sets or when we need to understand interactions across multiple time steps. Knowing the common techniques in time series forecasting is great, but how do you know which one to choose? Choosing the right method depends on your data complexity, goals, and resources. But generally, for smaller data sets with trends or seasonality, statistical methods like regression and ARIMA are efficient, interpretable, and work well with limited computational resources. When time does not need to be sequentially represented for predictions, use machine learning models like SVR. These also tend to be more interpretable than deep learning models. For more complex or large data sets, deep learning models like LSTM and transformers capture intricate dependencies, but could require more processing power and larger data sets for training. And when your data has repeating cycles or sudden spikes, signal processing and wavelet methods can help to better understand noise or isolate specific frequencies. And if you're still not sure which method is right for you, try it all. MATLAB has apps for data processing, signal analysis, machine learning, deep learning, so you can try all of these methods quickly and see what makes sense for your project. For more resources and other videos like data preprocessing with MATLAB, check out the links in the description. Thanks for watching. I'll see you in the next video.